Imagine you're the global supply chain manager for Bean and Brew, a rapidly expanding coffee empire. Your mission: ensure every single coffee shop, from bustling New York to serene Kyoto, has the perfect blend of Arabica and Robusta beans always. But here's the challenge: you're tracking current inventory, daily consumptions, and upcoming shipments across three continents: North America, Europe, and Asia. Suddenly, a critical alert flashes: a potential shortage of Robusta in Europe, while Arabica is overstocked in Asia. How do you quickly make sense of this mountain of data and make crucial decisions before the coffee runs out? This isn't just about coffee, it's about making sense of interconnected data efficiently. To tackle this data overload, mathematicians created a powerful tool: the matrix. Simply put, a matrix is a rectangular array of numbers, symbols, or expressions arranged in rows and columns. It's like a highly organized spreadsheet, but designed specifically for mathematical operations. Each number within this array is called an element or entry. In our coffee crisis, we can represent our current inventory as a matrix where each row is a region and each column is a bean type. See how neatly our complex data now fits into this structure? Now, every matrix has a specific size or dimensions, also known as its order. This is defined by the number of rows and columns it contains. We always state the number of rows first, followed by the number of columns. So a matrix with m rows and n columns has an order of m by n, written as m times n. Our coffee inventory matrix, for instance, has 3 rows and 2 columns, making it a 3 by 2 matrix. This order tells us exactly how our data is structured. A special type of matrix is the square matrix. This is simply a matrix where the number of rows is equal to the number of columns. So a 2 by 2 matrix, or a 3 by 3 matrix, or an n by n matrix is a square matrix. While our coffee inventory matrix isn't square, a square matrix might be used if, for example, we were tackling inventory for 2 regions and only 2 bean types, leading to a 2 by 2 arrangement. For any square matrix, we have something called the main diagonal. These are the elements running from the top left corner down to the bottom right corner. Think of it as the elements where the row index is equal to the column index. While our main coffee inventory matrix is in square, understanding the main diagonal is crucial for future matrix operations and concepts like determinants, which you'll encounter in higher level math. Now, let's look at specific data points. A matrix with only one row is called a row matrix, or sometimes a row vector. For instance, if we only wanted to see the inventory for North America, we'd extract its row, 250 units of Arabica and 180 units of Robusta. This single row forms its own matrix, a 1 by 2 row matrix. Row matrices are frequently used in various applications, including transformations in geometry. Similarly, a matrix with only one column is known as a column matrix or a column vector. If we wanted to see the total Arabica inventory across all 3 regions, we would look at the first column, 250, 300, and 150. This creates a 3 by 1 column matrix. Just like row vectors, column vectors are fundamental in linear algebra, often representing points in space or specific data attributes. Finally, we have the zero matrix. As its name suggests, a zero matrix is one where every single element is zero. it can have any dimensions. For instance, if there are no new Arabica or Robusta shipments planned for any region, our upcoming shipments data should be represented by a 3 by 2 zero matrix. The zero matrix plays a role similar to the number zero in arithmetic. It's the additive identity for matrices. Alright, now with our foundational understanding of matrices, let's solve the global coffee bean problem. We represent our data as matrices. Our current inventory, say matrix I, our upcoming shipments, matrix S, and our daily consumptions, matrix C. To find our projected new inventory, we simply add the shipments to our current inventory and then subtract the consumptions, all element by element, following matrix addition and subtraction rules, which we will cover in the next lesson. First, let's add inventory and shipments. Then we subtract the consumption from this total. And there it is. Our new inventory matrix. North America has 260 Arabica, 250 Robusta. Europe, 250 Arabica and 250 Robusta. Asia, 245 Arabica and 200 Robusta. This concise matrix quickly reveals our global status. The original alert about Robusta shortage in Europe, we now see that even with shipments, Europe's Robusta is at 250 units, requiring closer monitoring, confirming the initial concern and allowing us to act. Matrices make complex data manageable. Now, from our tangled web of numbers, we brought clarity using the elegant structure of matrices. This isn't just theory. It's the bedrock of how companies manage logistics, how graphics card render 3D words, and even how search engines rank web pages. Understanding matrices is a powerful step into advanced mathematics and its real-world applications. If you found this insightful, hit that like button, subscribe, and tell us in the comments what real-world problem you think could be solved with matrices. Join us in our next lesson where we'll dive deeper into matrix operation, addition, subtraction, and scalar multiplication. Keep exploring and keep solving. Thank you for watching.